Hello, welcome to the Unit 9 podcast on section 19.4. Today we're going to be discussing neutralization reactions. I'm Mr. Sakaguchi.
I'm Mr. Lin.
Here we go. Reactions between acids and bases result in neutralizations. This is a specific kind of double replacement reaction where an acid and a base react to produce salt and water.
So every single time an acid and base cancel each other out, you will produce salt and water. The classic vinegar and baking soda, that crusty white stuff left over, salt. When you look at the complete and net ionic equations, you'll realize that water is the net formed product.
And also be aware that the higher the concentration of the acid and base in the neutralization reaction, the more violent it is.
Right.
We can do something known as a titration with acids and bases, and this is a method for determining the concentration of a solution by reacting a known volume of the unknown solution with another solution where we know what it is and what the concentration is. So, for instance, let's say we had a 2-liter solution of hydrochloric acid, but we didn't know the molarity. And let's say we take a sample of it and we neutralize it with sodium hydroxide at 1 molar.
And since we know the amount of sodium hydroxide that we used to neutralize it, then we can figure out what the concentration of that acid is.
So if we look at the reaction, the neutralization reaction between HCl and NaOH, notice that there's a 1-to-1 molar ratio. So if I know how many moles of NaOH I added, I know that's equal to the same number of moles of hydrochloric acid.
Right.
So if I multiply, if I take the moles of HCl, once I know the moles of NaOH, I can figure out the moles of HCl, and I can divide that by the original volume of our hydrochloric acid, and that'll give me the molarity of the original solution. Mm-hmm. That's basically what we're doing. A few other things about titrations. How do we know when something is neutralized? We have to use a measure to help us know when we get to that point. And we use either a pH meter or we can use indicators, preferably both. What we're looking for here is we're looking for the equivalence point. The equivalence point is basically where the moles of H plus and the moles of OH minus are equal. Mm-hmm. The pH will stay relatively stable until you get to this endpoint, equivalence point. Basically, you'll see a stabilization or a steady either increase or decrease in pH, and then all of a sudden it'll spike either dramatically up or dramatically down.
Right. So it's stable, and then when it spikes, there will be a huge change in the pH. And if you have the indicator present, it's usually done visually. You'll notice a change in color. Or if it's on using a pH meter, there will be a rapid shift in the numbers.
Yeah, so we try and choose endpoints or indicators that have endpoints close to the equivalence point of the neutralization reaction we're interested in. And while you might think that everything would neutralize at 7, not everything does. And this is because of the relative strengths of the acids and the bases themselves.
Right.
Okay. So how do we calculate molarity from a titration? Well, what we do is we write out the reaction, then we calculate the moles of titrant. What?
That would be, in the case, in the previous example, that would be our moles of sodium hydroxide that were used.
It could be base or it could be acid, so
right.
It could be either depending upon the way the question's written. So we can figure how much of the titrant we added by multiplying the volume by the molarity. And then we can use the mole ratio from the balanced equation to calculate the moles of our unknown. And then we can divide by the original sample's volume to figure out the molarity.
Right. And once you have that you've got your molarity concentration.
Okay. And here's an example. So let's say we had CSOH solution and we don't know the concentration. And let's say we take 30 milliliters of it, and it takes 26.4 milliliters of a 0.250 molar solution of hydrobromic acid.
So since in step 1 you can see clearly that the ratio of hydroxide to hydrogen ions or acid to base is a 1-to-1 ratio. So we know that however many moles of hydrobromic acid are used, that's how many moles of hydroxide or base are in the solution.
So we can calculate moles of hydrobromic acid by multiplying them the molarity of the solution by the volume added for neutralization. So it's 0.250 times 0.0264. So remember, this has to be converted into liters by dividing by 1,000.
Right.
And then we get this, this is how many moles of HBr is present. And because of the 1-to-1 stoichiometric ratio, we know that if this is the amount of acid added, this has to be equal to the amount of CHOH present.
Right. And since we know what the number of moles of CSOH are, we divide that by the original volume of our unknown base, and we get a concentration of 0.22 molar CSOH.
We also have salt hydrolysis. So some anions from some dissociated salts are capable of accepting hydrogen ions from water and forming different kinds of acid or bases. Similarly, cations from some salts can release hydrogen ions into water.
And you can figure out which ones are going to affect the pH in what direction, generally by looking at what the products are. So if it's producing hydroxides or hydrogen ions.
Well, this is after the fact. They're going to need to, well, how do I know this could happen in the first place?
Right.
So if we're looking at anions, anion is going to be the conjugate base of some sort of acid, right? And if I combine the anion with hydrogen ions, I'm going to get some sort of acid HX. Now, if HX is a strong acid, then it's not capable of splitting water, and you don't have to worry about any of this happening. But if HX isn't strong, then it means it's a weak acid, and if it's a weak acid, the X minus is going to react with water to produce this and this. Now remember, if this is a weak, remember the conjugate base of a weak acid is strong, so this is the conjugate base, which is strong, which means it's going to have a high affinity for the hydrogen ion.
Right.
If you remember your Bronsted-Lowry stuff, resulting in the formation of the weak acid and hydroxide ions.
Right.
Okay. Ions that still have ionizable protons can be amphiprotic, which means they can act as an acid or as a base. So those are special situations where we'd have to look at either Ka or Kb. But for the most part, we're not going to have to worry about them at this level.
Yeah.
For cations, again, these are polyatomic cations whose formulas contain at least one proton or greater than one can consider conjugate acids of weak bases. And remember, conjugate acids of weak bases are strong, which means they're going to want to give up that hydrogen ion. Ions of alkali metals and heavy alkaline earth metals do not react with water and will not affect pH. You'll often find these cations in strong bases, so you don't have to worry about those.
Buffered solutions. Buffered solutions are solutions that resist pH change. So when you add more hydrogen ions or add an acid or add a base in a certain amount of quantity, the pH is not going to shift. We have something like that in our blood to maintain a steady pH within our own system at all times. And it's composed of a weak acid with a conjugate base or a weak base with its conjugate acid.
So what ends up happening is the conjugate acid or the base, conjugate acid or the base, or the conjugate base and the acid will counteract the formation, will counteract the addition of either or. There are a lot of natural buffering systems actually in your body to keep your body's pH stable. For instance, in your bloodstream and in your stomach and other places as well. In terms of choosing a buffer, if we're creating our own buffer system, we always want the most optimal buffers are ones where there's equal amounts of acid or base and its conjugate.
And what you're going to do is look up the Ka value of the compound and then take the negative log of that to find the pKa. And you want your pH and pKa to match up pretty close to each other, and that would make it a pretty good buffer.
Yeah, so that way you know the range the buffer system will work in that's close to what you want for the pH. I think that's it.